The 1911 Nobel Prize in Physics was won by this gentleman, Wilhelm Wien, who was originally from Prussia, which is now part of Russia, eventually wound up in Germany, where he passed away in 1928. But in 1911, he won the prize for his discoveries regarding the governing of the radiation of heat. Now, that's a big, fancy scientific pile of words that basically said this guy understood how heat works better than just about anybody else at the time. Whether that's how fast does it radiate out of metal versus glass versus large surface area versus small surface area, to how can we predict the temperature of something based on our observation. These are an interesting set of things that actually have application in our world today. So let's dive in. I warn you, there's going to be a little bit of math today, but that math is important and we're going to try to make it as easy as we can. This basic equation, which was his law for governing the radiation of heat, basically says the peak wavelength of radiation is equal to a constant, which is just a consistent number used on every equation, divided by the temperature. So it shows that the wavelength of radiation emitted from something and that temperature are related by this equation. And what that does is it lets everything from the little infrared sensor an air conditioning technician uses to check whether or not your air conditioner is working properly, to a heat-seeking missile finding its target, is governed by this equation here. Now, it was later refined by Max Planck and some others, but this is the basic equation that led to other work like Planck's later on in the 1900s, which then led to the development of quantum theory. So this equation, well, it's very simple and it just talks about heat. Heat is a very important thing that lets us understand all kinds of stuff in the physical realm. Now, wait a minute, that was a lot of math, I understand. Now, what that really means in English is if you heat something up, you will see different forms of radiation coming from it. And electromagnetic radiation, whether it's a microwave or a light wave or an infrared wave or even an X-ray, it all moves the same. It's just different wavelengths of that same stuff. Sometimes our eyes, if we see something in the right wavelength range, can interpret it as different colors. And as it gets hotter and hotter, the color characteristics will change. Sometimes it's in the infrared, sometimes it's in the microwave, sometimes it's in the visible spectrum. As you can see here, if you heat it hot enough, you get something that turns into orange, maybe yellow, and those different color zones are actually different temperatures. Some are hotter than others. Now, what the heck does the color have to do with the temperature? Well, wavelength, whether it's light or microwaves or whatever, is just one wave, one crest to crest of the wave as it travels through space. So on the top chart, you can see what a wavelength looks like if you graph it out. On the bottom, what you're seeing is peaks of blackbody radiation at different wavelengths. And the further you go into longer wavelength regions, what you're getting is lower temperatures. So if you see something in the visible instead of like the infrared, which is outside of the human ability to see, what you'll find is it is much more hot than something that's down in the infrared. Now, our eyes have evolved to be sensitive in certain wavelength regions because that's what the surface of our sun gets through our atmosphere. So we are sensitive within certain regions between 400 and 700 nanometers. Electromagnetic radiation exists all the way from that range, a little bit shorter wavelength, all the way out to the meters that let our FM and AM radios work, as well as CB and everything else that we transmit. Cell phones, you name it, it all travels at different wavelengths. So the fact that we can see some of them is kind of interesting. We can't see all of them, obviously, but the longer the wavelength, the cooler that temperature is. Now, what the heck does that have to do with thermal guided bombs? Well, it should be pretty simple to tell at this point, right? Let's take a look. Now, this is a thermal engine of a fighter jet flying past. It's publicly available out on the internet for anybody to see, and to no surprise, the exhaust and the engine are the hottest things in the air. So when you see movies like Top Gun and they fire a missile and then the person in the other jet tries to evade by firing flares, what's happening is they're trying to confuse the missile into thinking something else is the jet. So they put a flare out there that looks like the jet. It says, no, go chase that, right? And sometimes the missile evades and goes and finds the flare. Sometimes it doesn't. But what they're trying to do is confuse that seeker in the front end of that missile. Same thing works with thermal guided bombs as they approach the ground, but it's all because of the work a physicist did in the late 1800s. Thermal imaging is a highly useful subject far beyond this. For instance, you can do it in fields well outside the military. When trying to determine what areas of your home may benefit from some better thermal insulation, whether it's to keep cool air in, hot air out, hot air in, and cool air out, you can use the same type of thermal imaging to look at the house and go, oh, okay, well, that's the area where all the thermal energy is leaking. It's a very efficient method of doing it, especially if you're doing a home inspection on a house you're trying to purchase, if you're trying to figure out how to upgrade insulation, if you're trying to figure out how to be a better house designer. You can use this type of information to work backwards into a solution. So work done in the late 1800s is something, once again, that impacts everybody's life every day. This same thing works in lots of different applications. This is just a few of them. If you're curious, just Google it. You will come up with more hits than you know what to do with. Hope everybody has a great day, and I hope you've enjoyed this video. Click subscribe, and don't forget to hit that like button. Have a great one.